In exercise 12.8, we're continuing our exploration of how to change the number of carbons in a multi-step synthesis. And the principles that we learned from the previous video, the sort of pattern that we picked up on, is that if you want to add carbons, use a terminal alkyne, treat it with sodium amide, that will turn it into a nucleophile, and then just add an alkyl halide, a carbon chain with a leaving group on it, a halogen leaving group on it, in order to do an SN2 reaction. And that creates a new carbon-to-carbon bond. So overall, you would do a two-step procedure. First, take sodium amide to a terminal alkyne, and then react it with an alkyl halide. And the R group, that's any carbon chain, that just depends on what carbon chain you want to add to your alkyne. And the X represents any halogen, so chlorine, bromine, or iodine. That's how you add carbons. If you want to remove carbons, you can do ozonolysis. So that that's with an alkene, you do O3 followed by, in a separate second step, dimethyl sulfide, DMS. And that will saw away a double bond and turn it into two double bonds to oxygen. And so if you're just looking at one half of the molecule, it looks like the other carbon on the other half got removed. So if you're trying to remove carbons, you can do ozonolysis. If you're trying to add carbons, you use these terminal alkynes. That's the big principle we're going to apply with other reactions in exercise 12.8. Okay, so first, let's check the number of carbons. We have 1, 2, 3, 4 on the left. We have 1, 2, 3, 4, 5, 6 on the right. So we have more carbons. That means we're going to have to add carbons. The only way we know to do that is to use a terminal alkyne. Now here we have our alkyl halide. You remember, in this reaction you need an alkyl halide, and here we have one. So we just need to get the nucleophilic carbon. We already have 4 carbons, we just need 2 more. So we can add a triple bond, and there's hydrogens on here, but that would be like carbons 5 and 6. And if we treat that with sodium amide, and let's say just one equivalent, that strong base will rip off this hydrogen, and the electrons in, and I should do it on the other side, that strong base will rip off this hydrogen, and the electrons in the bond that was holding the hydrogen will snap back onto the carbon. There'll be a lone pair, and that lone pair can act as a nucleophile. So once you have that, and here, that's what you get as the product. You originally just have the hydrogen there. So once you have that nucleophile, then you can take your molecule, your alkyl halide, and do an SN2 reaction. So that carbon nucleophile will attack this carbon here and kick the leaving group off. And so we'll form a new bond between carbon 4 and carbon 5. So what we'll have at this point is we'll have this, but instead of the bromine, which we'll have left, we will have this. Carbon chain there. So we have 4, this is now 5 and 6. So we have our 6 carbons, the 6 carbons we wanted. But now we have to change the functional group. So that hydrogen's still there, but it's implied. The hydrogen I erased, at the terminal, on the terminal alkyne. So there's that hydrogen there, that gets erased. It's still there, it's just implied in the skeletal structure. So we have our 6 carbons. We just have to turn this alkyne, that triple bond between carbon 5 and 6, into a double bond. In other words, we want to hydrogenate this. Now we don't want to use just pure hydrogen and platinum, palladium, or nickel, because that will take that all the way to an alkane. We could either use dissolving metal reduction, sodium and liquid ammonia, that's all one step, and that would take that to an alkene. Normally that would give us the transalkene. Normally that would give us the transalkene, but this doesn't come in a cis and transversion. It has 2 hydrogens on one of the carbons, so it's neither cis nor trans. So you could either use dissolving metal reduction, or you could use H2 with Lindlar's catalyst. That would usually give you a cis-alkene. But as we said, this doesn't come in a cis and trans version, so either one will take the alkyne to the alkene. So here we noticed that the number of carbons increased as we went from the reactants to the products. So we knew we had to use a terminal alkyne, sodium amide, and an alkyl halide. We saw that they gave us the alkyl halide. So we started with the terminal alkyne, and we treated that with one equivalent of that strong base sodium amide. So here we start with this molecule, and we first treat this with that ethyne, also called acetylene, in sodium amide. That rips one of these hydrogens off, turns it into a nucleophile that attacks our original alkyl halide and gives us this alkyne product. Then we just have to turn the alkyne into the alkene, and there are two ways to do that. We could either use dissolving metal reduction, so sodium in liquid ammonia, or you could bubble hydrogen gas through there and sprinkle in some of Lindlar's catalyst. Either one would work. You wouldn't use both, so just one of those. And that procedure, really just 2 steps, would be enough to create that, or to achieve that transformation. Okay, let's try B. If we look at the carbons here, the number of carbons here, we have 1, 2, 3, 4, with a methyl group coming off of 2. And here we only have 1, 2, 3, with a methyl group coming off of 2. So the number of carbons went down. Well, we only know one way to reduce the number of carbons, that's ozonolysis. The problem is, in order to do ozonolysis, we need a double bond, at the very least. And here we have all single bonds. So we can get a double bond because we have a leaving group. Now, so we can do an elimination reaction. Now, the carbon that has the leaving group on it, that's the alpha carbon, and each of the carbons next to it is the beta carbon. So theoretically, because we have 2 different beta carbons, we could do 2 different elimination reactions here. So if we take this, we could either do an elimination reaction toward the beta carbon on the left, in which case the bromine would leave, and you'd form a pi bond in this direction. Or you can do an elimination reaction toward the other beta carbon. The bromine would leave, and you'd form the pi bond in the other direction. Now, which one do we want? Well, we could see that the double bond to the oxygen, which is made from the double bond to the carbons in ozonolysis, is on carbon number 3. And that happens in this structure on the top right. And the other one, it occurs first on carbon number 2. So we really want this structure here. If we treated that, so first we need that. Now if you'll notice, that is the less substituted alkene. This alkene only has 1 carbon branch coming off of the carbons in the double bond. That is mono substituted. The other one, the one we don't want, has 1, 2, 3 carbon chains coming off the carbons in the double bond. That's tri-substituted. That more substituted product, that's the Zaitsev product. The less substituted product is the Hofmann product. So we want the Hofmann product. To get the Hofmann product, to form the pi bond toward the less substituted carbon, the less crowded carbon, we have to use a bulky base. And the poster child for a bulky base is potassium tert butoxide. So if we treat this original molecule with that bulky base, potassium tert butoxide, we'll end up getting this Hofmann product, this Hofmann elimination product, with the pi bond toward the less substituted carbon. And once we have that, we can do the ozonolysis. So because this is an alkene, we'd first use O3, and the second step for an alkene is DMS, dimethyl sulfide. That cracks that bond in 2 and replaces it with 2 double bonds to oxygens. Now, this molecule here is the smallest possible aldehyde. That's formaldehyde. That goes on and lives its own life. But you can see the molecule we're left with is the molecule we wanted. You'll notice that this has a hydrogen here. It's just implied in the structure that we had a second ago. Notice that if we had the Zaitsev product and we try to do an ozonolysis with that, that would crack this bond, and we would end up with 2 products. We'd have the product on the left, and we'd have product on the right. So notice, with ozonolysis, you sort of break the double bond. It still exists. It's just in 2 separate molecules where the carbon's connected in the double bond. Now they each go separately to 2 different oxygens. And that neither of those is the product that we want here. So the Zaitsev product didn't help us. We wanted the Hofmann product. So overall, the steps that we need here are, first, we needed the Hofmann elimination product. Or I should say, when we first looked at this, we saw that the number of carbons went down as we went from the molecule on the left to the molecule on the right. And so instantly we thought, eventually we're going to have to do an ozonolysis. And we saw the double bond to the oxygen there. That suggests ozonolysis too. But in order to do an ozonolysis, you have to have a double bond. And we don't have one here. What we do have is a leaving group. So we can use that to create a pi bond by doing an elimination reaction. We looked at the Zaitsev and the Hofmann products, and we saw that the product we wanted was the Hofmann product, so we used a bulky base to get that. A bulky base like potassium tert butoxide. Once we had the Hofmann product, we could do the ozonolysis. That's 2 steps. Because it's an alkene, the second step is DMS. If you have an alkyne, it's water. And that gave us our product. So overall, we just needed to add the original molecule with potassium tert butoxide to get the Hofmann elimination product, and then do ozonolysis, whose first step is ozone, bubbling ozone through there, and whose second step is dimethyl sulfide. So that recipe would be enough to transform that molecule to create or achieve the transformation that they're asking for here. Okay, how about with C? Now, if you look at the number of carbons, we have 1, 2, 3 in the molecule on the left, and 1, 2, 3, 4, 5 in the molecule on the right. So we have more carbons here, specifically 2 more. And that's a sign that we're going to need to use a terminal alkyne, an alkyne that has a hydrogen on one end. Here, we'll use an alkyne that just has 2 carbons, because that's how many we need to add. If we had more carbons, we'd use an alkyne with more carbons on it. But we just need to add 2, so we'll use ethine, which is also called acetylene. This is the gas that is used in welding torches. It burns very hot. And what we can do is we can treat that with 1 equivalent of sodium amide, and that strong base will rip off this hydrogen here. The electrons in the bond will snap back onto carbon number 4, where there'll be a lone pair with a full negative charge. In other words, we've turned that carbon into a nucleophile. And now we can do an SN2 reaction. This carbon number 4 can attack this carbon here and kick the leaving group off. So that what we have next is this alkyne attached here. Whoop. This alkyne attached right there. So that gives us our 5 carbons. Those are the 5 carbons that we needed. So now our carbon chain is looking good. I'm going to erase this hydrogen here. It's still there, but it's just implied in the skeletal structure. So that's good, but we don't have the triple bond here in the final product that we want. Instead, we have 2 bromines. So we need to add the bromines there. And not just 2 bromines, but if you notice, we only have 1 hydrogen on carbon number 5 in our current product, and you have 3 hydrogens on carbon number 5 in what we want. So if we get rid of the one that's there from the beginning, you can see that we add not just 2 bromines, but 2 hydrogens. Well, that's a sign that we use HBr, hydrohalogenation, specifically excess. That way we can add 2 bromines and 2 hydrogens, 2 equivalents of HBr. Now if we do this all by itself, it will be Markovnikov addition. If we use peroxides, it'll be anti-Markovnikov. Which one do we want to do? So let's look at where the hydrogens went and where the bromines went. The carbon that the hydrogens went on is only bonded to one other carbon, so it's primary. The carbon that the bromines went on is bonded to 2 other carbons, so it's secondary. The hydrogens went to the less substituted carbon. That's Markovnikov addition, and so we wouldn't add peroxides here. We would just add excess HBr. Oops, this should go down here. So, if we treat that alkyne with excess HBr, we will end up getting our product. We'll add 2 hydrogens and 2 bromines. The hydrogens will go on the less substituted carbon, and the bromines will go on the more substituted carbon. So overall, to make this transformation happen, we saw that the number of carbons increased as we went from the left to the right in the synthesis. So we knew we had to use a terminal alkyne. We used a terminal alkyne that had the same number of carbons as the number of carbons that we needed to add, 2. We treated it with 1 equivalent of sodium amide, and that turned it into a nucleophile. Then we added our alkyl halide. They did an SN2 reaction and attached. Now we had our 5-carbon chain. We compared that with our product and noticed that in the product, 2 HBRs were added. So we added excess HBr. We noticed that they were added Markovnikov, so we did not add peroxides. And the overall synthesis is first to take ethyne, also called acetylene, and combine it with 1 equivalent of sodium amide, NaNH2. Then you react that with your alkyl halide, and that brings us here. And in the second step, to use excess HBr, and that adds 2 equivalents of HBr in a Markovnikov way, and gives us our final product. So the synthesis really just has 2 steps, and with those 2 steps you can achieve that transformation. So in this video and in the previous video, we've explored how to change a carbon chain. To increase the number of carbons, you use a terminal alkyne, sodium amide, and an alkyl halide. To decrease the number of carbons, you use ozonolysis. And you can combine those patterns with the other reactions that we've learned to do more complicated, more exciting, more inspiring multi-step syntheses.